Okay, today we'd like to talk about how to design an airplane configuration using an Excel spreadsheet. So this is a very simplified way to design an aircraft configuration, a way to get started. It doesn't go into all the details that you'd really need to go into to design an airplane, but it's just a good way to get started. So this project will provide a video that will demonstrate how to design a conventional airplane configuration. So in this demonstration, the Piper Cub J-3 airplane design will be evaluated using a spreadsheet as an example. For other aircraft configurations, a similar process can be used. There are many good books out there that provide greater details on aerodynamics. However, this is a simplified design process that is good to use to get started in investigating your particular aircraft's design. Once this is done, then aerodynamic models with greater details can be added to the spreadsheet. So the following procedural steps are used. So the first step is to gather parametric data on the aircraft. If you don't have that already, or if it's an existing aircraft, you may be able to find it in the public domain. If it's something you're working on, you might have to generate that. So for our example here, the Piper Cub J-3, we'll take a look at some of the material that I found on the internet that I'm using for this example. So one thing I found is I found this Piper Cub checklist that has some information on it. Some of the things are the weight, and some of the things that are interesting. The top speed is 83 miles an hour, so it's not a very fast aircraft. As you go to higher speed aircraft, this process might not work as well, but for a low speed aircraft, laminar flow, this process works pretty good. So here's some information that is helpful. Another useful thing that I found on the internet is I found an owner's manual for the J3C 65 model of the Piper Cub, and it has some interesting information that was very helpful for this analysis. Some of the preliminary information that you get as I'm paging through this. So this process is kind of independent of airfoil. We're assuming a flat plate type of airfoil. So I found this to be somewhat interesting. It has a nice drawing of the aircraft with different parts pointed out. Some of the parameters that were very useful are the wingspan, the chord, wing area, incidence. Some of this information here, the dimensions are very good to have, and it goes into some more additional information here that could be helpful. Parametric information that could be helpful. So this is a whole manual, 27-page long manual that has information that you may be able to squeeze out that would help you analyze a design. If you're designing your own configuration, then you would have to get this from other sources or estimate, what your wingspan would be, your chord. It's kind of a trial and error method where you would actually be putting these parameters in to try to get the best design. The next thing is to draw a figure of your airplane configuration. So the equations will depend on the configuration factors such as the number of control surfaces, lifting surfaces, and engines. You'll need to adjust this for the configuration that you have selected. So I did, if I page down here, I did make a nice drawing of the aircraft. Let me zoom on this a little bit, zoom out a little bit. So some of the interesting things, okay, so this is a little drawing, not to scale, I made of the Piper Cub aircraft, and what I started to do is name things, like this is the wing, this is the fuselage, this is the stabilizer, the non-moving part, and the elevator is the moving part, and the airlines are moving parts, and the fin is kind of the fixed part of the rudder, and the moving part I called the rudder. So you want to give things names and dimension things out. Start off with a picture in your mind of what your configuration is. So your configuration might have two wings, it might have canards, it might have all different types of extra engines and propellers. So that's the elements that you want to make a picture of because you're going to need to add up all these aerodynamic components to get a good indication of what's going on in your design. So the things we're going to do for this analysis is we're going to compute the lift from the non-movable surfaces such as the wing, stabilizer, and fin. And then we're going to compute this drag factor. It's called the D1 drag. That's what I'm calling it. That's the non-movable surface drag from the wing, stabilizer, fin, airline, elevator, rudder, and fuselage, and whatever other components you may have in your design. And then compute the D2 drag. That's the movable surface drag. So that's the drag from things that move, such as airlines, the wing, which moves in with angle of attack. The D1 drag isn't a function of angle of attack where the D2 drag is, and anything that moves is D2 drag that moves an angle. So the next step is to compute the moments from the airline, elevator, and rudder, and compute the thrust from the engine would be the next step. And then we want to compute the inertias, IX, IY, IZ. Those are the inertials of your mass of your aircraft. So we sum up the forces and moments, and we're going to just use 2 pi for the coefficient of lift. This is the flat plate assumption, so we're assuming there's no airfoil. As we get into more detailed models, then our coefficient of lift might not be 2 pi. It might be something different depending on the airfoil. But for a flat plate, 2 pi is a good value for the coefficient of lift. So we're assuming a small angle of attack for coefficients of lift and coefficients of drag, and we're not in stall conditions. So this is kind of limited to small angle of attack, small side slip. But it's a good way to start if you're doing an initial design. So I have some notes here. The D1 drag is drag that's not a function of angle attack or control surface deflection. And D2 drag is the drag that is a function of angle attack and control surface deflection. So the following procedure assumptions are used to get one design point. So one thing to do is to get one design point and put that in a spreadsheet to verify your calculations. So you get the one design point, then put this in a spreadsheet, and then you could add columns of them to do a parametric evaluation. So you could take a look at the design to see if it's feasible or not. Again, here's the basic steps on how to design an airplane. So you want to draw a picture of the plane and then write the basic aerodynamic equations for lift, drag 1 and drag 2. So you want to write the equations to sum the total forces x, y, z, and the moments L, M, and N. So the next step is to vary the parameters to show the X force is strong enough for forward flight and the Z force is strong enough to lift the plane's weight. If so, then the design is feasible. So the next step is to vary the parameters to show the moments are reasonable to be able to control the aircraft. And the next step is to compute one design point by hand calculations. This result will be used to verify the equations using the Excel spreadsheet. So once you get that one point done, you can put it into Excel. You do the one design point by hand calculations, and you put it in Excel to verify it. And then from there, we could copy the columns to do parametric variations. So over here, it shows a nice little picture of what we're going to try to do. So this is our plane. We have an x-axis, which points with the nose of the plane, the y-axis, which goes through the right wing of the plane, and the z-axis, which points down to, say, the center of the earth. This is like on the body axis, really the body axis of the aircraft. So anyway, what we have is we have this x, y, and z coordinate system. So what we want to do is we have our force, say we have a propeller here, so we have a thrust force and a drag force along the body of the aircraft, the longitudinal part of the aircraft. So we want to verify that we can at least generate our thrust is greater than our drag so we can move forward. Otherwise, it's not a feasible design. If we can't get enough thrust to counteract the drag, we can't move forward with this aircraft. Unless it's a glider or that type of thing where it's initially pulled. But anyway, we want this aircraft to fly on its own. So we wanted, so the one part of this task is to verify our thrust can be made greater than our drag. And the other part, the other task is to verify that our lift is great enough that we could overcome the weight of the aircraft. So that's an important part of it in our z-axis, okay? So in the lateral part, in this case, our y is going to be 0. If we have more advanced models, then y wouldn't be 0. But the other part of this is to verify we have L, that's our rolling moment. We have M as our pitching moment, and N is our yawing moment. So we want to verify that these make sense, that we could generate enough moment from our control surfaces to reasonably roll the aircraft, pitch the aircraft, and yaw the aircraft. So that's the other thing we're going to do in this analysis. So we're going to start off with the most basic aerodynamic equations to get started with this. So we're going to assume our coefficient of lift is 2 pi. That's basically the coefficient of lift for a flat plate in laminar flow. And another very important equation is dynamic pressure, which is equal, Q is equal to 1/2 rho v squared. So we're going to be using that equation. So we have a lift equation. So the lift is the coefficient of lift, which is 2 pi times the dynamic pressure Q times the surface area. So this is our equation for lift. And the next important equation is angle of attack. So generally, we're going to just look at very small angle attack, maybe nothing more than 5 degrees, and also side slip, nothing more than 5 degrees. So angle of attack is the forward velocity over the vertical velocity, the inverse tangent, and side slip by definition is the lateral velocity over the total velocity, the inverse sine. So our total velocity is the sum of these three velocities, u, v, and w, in the body axis. So if we go back to our picture, this is u, is the velocity along the nose, and v is the lateral velocity along the right wing, is positive, and w is our vertical velocity, positive is downgoing. So that's our basic equations. So one thing I found helpful was this chart that I found that has different drag coefficients for different shapes. So for a flat plate, if you use 1.28, that works pretty well. And for airfoil, 0.045. So it's like 4.5%, I guess, of the dynamic pressure goes into drag. And the bullet shape also, that is good for a nose. It's 0.295, like an airfoil, say a wing, 0.045, and say for a flat plate, something like that, maybe that would be like a control surface is 1.28. So I found this to be pretty helpful, where A is the frontal area. So this is a good way to figure out coefficients of drag and the drag force. So anyway, so we have drag of an airfoil is 0.045. Drag of a flat plate is 1.28, and drag of a bullet is 0.295. So the drag force would be this coefficient of drag, possibly one of these, times the dynamic pressure, times the surface area. So the one thing we want to do is compute a single design point that we could put into our spreadsheet just to verify our calculations. So we're going to assume our airspeed is 100 knots, and we're going to figure out what it is in feet per second. So that's equivalent to 168.77 feet per second. So air density at sea level, we can get that from the standard atmosphere table, and we're going to take a look at that a little bit later into this video. So this is the density at sea level in pounds seconds squared per foot to the 4th power. So we're going to compute our wing area for the Piper Cub, and this is our wing area. And we have the movable ailerons. A single one, we need to get the area of that. So that's 9.4 square feet. So we can compute the stabilizer. So this is the stabilizer area, and then we also wanted to get the wing area with no ailerons. So we subtract 2 times 9.4 off of the total area, and we get a reduced area there. So we're figuring out these surface areas that we need for our lift and drag equations. So we have the elevator movable area. That's the part of the elevator that moves. The stabilizer is the part that doesn't move. So this is the movable area, and then we have our fin. So this is the non-movable part of what we might call the rudder, and then we have the rudder movable area. So this is taken off that drawing. So we go back to the drawing to get these dimensions, to get these surface areas, and then the fuselage area is, we're assuming that it's about 15 feet squared. It's maybe 60 inches by 36 inches. This is a good guess. We kind of drew that out on our diagram. So anyway, the dynamic pressure at 100 knots at sea level winds up being 33.8541 pounds per square feet. So our lift from the wing with no ailerons, this is the lift as a function of angle of attack. So it's 2 pi q s alpha's angle of attack. So when we multiply all those through, we get 35,321 pounds per radian of aileron times the angle of attack. So this is the wing itself without the aileron. So the lift of the wing is a function of angle of attack. Now a lot of times you'll see the lift at a certain angle of attack reduces because the wing is stalling. So this is assuming it's in the linear region where it's not stalling. So we compute, or we call our D1 drag is the kind of the fixed drag that's not a function of angle of attack. So we're using this, we're assuming it's a flat plane, a flat plate. So this would be our drag force. It winds up just from the wing itself at 100 knots, comes to 252.97 pounds, and then we have the drag of the wing. That is a function of the angle of attack. So this is our fixed drag, and this is a function of the angle of attack. So we're assuming it's a flat plane, a flat plate. As alpha deviates around 0, so that comes to a high number there. So then we have lift from the stabilizer. That's the fixed part of, say, the elevator, and that's a function of angle of attack. And then we have drag from the stabilizer. That's kind of our fixed drag, just assuming it's an airfoil that has a 0.045 drag coefficient. So that comes to lower 35.41 pounds. And then we have drag, or D2 drag from the stabilizer. D2 drag from the stabilizer is based on the surface area and the flat plate drag coefficient. And then we have lift from the fin. Now this is a function of side slip rather than which will cause a moment, rather than a function of angle of attack. So that's the lift of the fin. So we're just generating these numbers that we could check out in our spreadsheet, kind of like a baseline case. So this is our drag from the fin, D1 drag, and this is our D2 drag from the fin, and these are a function of side slip. So the fin is the part of the rudder that doesn't move. So now we're going to figure out our force moment D1 and D2 from the ailerons. So we're assuming equal and opposite motion from the ailerons. So basically, this would be the force here for one aileron, which is a function of the aileron angular motion plus the angle of attack. So we're assuming the torque is the angle of attack part cancels out, because there's 2 of them, one on each side, that are working opposite way. So this is the torque of from the aileron, and this would be our drag. So we have 2 of them, our D1 drag. So it comes to some small 28 pounds, our fixed drag, and this is our movable drag. And likewise, the angle of attack cancels. It's just the drag function of the deflection of the aileron. Okay, so the next part is force moment, D1 and D2 from the elevator. So the elevator is a function of angle of attack and deflection of the elevator. So this would be the force computed, and so the torque is the force times the length. It's a crank arm. Just the aileron also has a crank arm. So the torque winds up being a number. It's the angle of attack plus the deflection of the elevator. So next we have the fixed drag of the elevator. So it winds up being about 26.66 pounds, assuming it's an airfoil. And then we use our flat plate assumption for our movable drag. That's the movable the part of the elevator that when as it moves. So so we have a torque, and we also have our D1 and D2 drag. That's a function of the deflection of the elevator plus the angle of attack. Next we have the force from the rudder, and there's only one movable rudder on this configuration, so we figure that out. That's a function of the deflection of the rudder plus the side slip angle. And so the torque is also a function of the rudder and the side slip angle. So we have our D1 part, that's our fixed drag, and then we have the movable part that is a function of the deflection of the elevator plus side slip. So we also have the fuselage. So there's a fixed drag, assuming that it's a bullet shape, that it winds up being 152 pounds. And then we have our D2 drag, and we're assuming it's a function of that angle of attack and side slip of the two that also causes a drag force on the fuselage. So the next part here is our propeller. Okay, so I'm going to probably do a video in the future about propellers and how you can get the thrust from the propeller. So the propeller I found on the Piper Cub is a 72-inch diameter by 46. So 46 is kind of like the advance ratio. When you buy propellers, you buy by the diameter times advance ratio. So we're assuming the propeller is a 72 by 46 at 2,500 RPM. So there's some information here. We have the chord of the prop averages about 5 inches, and the radius is half the diameter, is 36 inches. So to compute the pitch of our prop, we know what this advance ratio is 46. So that means for every turn, it pushes 46 inches of air. So for every one turnaround, it's like a screw that's pushing 46 inches of air. So our pitch of the blade, if you go through the trigonometry, comes out to about 11.5 degrees, and our angular rate of the prop is 2,500 RPM, winds up to be 261.0 radians per second. So I came up with this equation. I'm going to give a video in the future about how to look at propellers and helicopter rotors, which will be helpful. I'm hopefully going to do another series on this, on how to design a helicopter in a similar way to this. So anyway, there's an average Q, dynamic pressure of the propeller. So it's rho times omega squared times the radius of the prop square over 6. So the dynamic pressure is 1.69 pounds per square inch of propeller. So you could actually get a thrust. The thrust from that winds up being 764.95 pounds. So so our air velocity is running 1,916 inches per second, and the power, we could do a power calculation, is 222.164 horsepower, which is typical for the type of engine that might be in a Piper Cub at max power there. So we're going to try to do another video in the future on propellers and helicopter rotor. Now we're going to do a weight breakdown, weight and moment of inertia, try to compute the moment of inertia of our aircraft. So we know The total weight of the aircraft is 1,000 pounds, and the fuselage weighs 700, and the wing weighs 300. So we have these masses in pounds, but we also want to look at it in pounds second squared per foot. So we divide it by 32.2 foot per second square. So we have some crank arms here to try to figure out our moment of inertia. So this one is about 2.5 feet, and the wing is 17.604 feet for our Piper Cub. So we're trying to figure out the moment of inertia around the x-axis here. So for a cylinder and a thin rectangular plate, there's some equations I looked up in a book and added the two together to get our moment of inertia around the x-axis. So this is going to be important to figure out our moments, or if our moment forces are reasonable. So we get 308.541 foot-pound second squared for our IX. In a similar way, our moment inertia IY is around the wing. So we're assuming our center of gravity is right in the middle there. So we come up with some equations for IY. So IY winds up being 300.19 foot-pounds second squared. And the last one is IZ. That's the moment of inertia, like our yaw moment of inertia. So that winds up being IZ winds up being 540.79 foot-pounds second squared. So I'm assuming our angle of attack is small. We have a little deflection. We have a positive angle of attack and a negative deflection of our elevator, and everything else is zero. Our side sub zero, our airline zero, and our rudder zero. So we want to sum up all the forces. So all the x forces is equal to the thrust minus all these drags. So if we could show that our a positive XF, if our thrust has to be greater than all of our drags to get forward motion of this plane. So I came up with that one point. If we sum all of our x forces, I wound up with 79.32 pounds, which is just a little bit of positive to get some forward acceleration. So in this model, we're assuming our y force is 0, and our z force, our lift at that point is 616.46 pounds. So we don't really have enough lift at this point. We need to get more angle of attack. We have 383. When it's positive, that means it's a downward force, so it's pulling the aircraft downwards. There's not enough lift here to lift the aircraft in this case. But anyway, that's our design point there, just to do our calculations. And of course, at this point, all of our moments are going to be zero because we don't have any control surface input right now for this case. So anyway, this is our Excel spreadsheet. So the first thing I have in my Excel spreadsheet is just a standard atmosphere. So I was able to download it from this website here, and you can get this from many different sources. So anyway, what I did is I took our hand calculations now, and I went and I put this in a spreadsheet. And so I made one column. This is the parameter, and this is the value. So you want everything in one line. So anything in bold is like an input, and anything that's not bold is computed. So this is our 100 knot case at sea level. So different things we could vary. Yeah, we could vary the prop diameter. We could vary the wingspan. We could vary all these parameters. And look at our design. So this is called base at 100. I made one called base at 100 and base 80. So, but the base 100 is relative to the hand calculations. So I went and I compared this against the hand calculations that we did in here, and they all match. So the one thing when you do a computation here, I have all the values in the B. So B is, there can only be, like for the variables, it can only be a B. So you don't want, you want the dollar sign in front of the number. So when you copy it to other columns, the B will vary. So if I move it to this column, if I take this now and I copy it and I paste it in the C, so now over here this will be C7 instead of B7. So if I say I change the airspeed, say I went to 80 knots, it updates only the things that have to do with airspeed. So you can see, yeah, the dynamic pressure is lower. So anyway, you want to get everything in one column, and that's the whole trick to this. So I have every computation I did by hand. I tried to color them a little differently to make it a little bit easier to work on. So anything in bold you could vary, and anything that's not bold, you can is computed. So one thing I have in here, the main criteria. Okay, this is our X force and our Z force. So you can see our X force, yeah, is positive. It's the 79.32 pounds. If I go back to our hand calculations and look at that, yeah, here's the 79.32, and our Z force is 383.54. So I want to go back here, and you see our 383.54. So you want to make sure those two match. So in our column here, yeah, there's no dollar sign in front of the letter, but in front of the number you want a dollar sign. So that means it kind of locks it in Excel. So the next spreadsheet I made is I varied the airspeed all the way from 0 to the only thing I changed to 150 knots. That's the only thing I changed here is airspeed. So I made a whole bunch of columns here. So this is a table now that I could use if my airspeed varies. How does that impact the lift and drag? And so what I did is I did it for all these points, and then I made some made some plots here. So I did it for a different angle of attack. So here at our design point was the 1 degree angle of attack. So I made these green where the positive, that means I can generate a positive, this is our X force and this is our Z force. And when this force goes negative, it means I can't, my drag is too high that I can't overcome the thrust of the propeller. So likewise here, this is our Z force table. And when that's positive, it means I can't lift my own weight. But when it's green and it's negative, it means I can lift my own weight. So at these higher airspeeds and higher angle attack, I could generate lift. Now where it's yellow, that's where these two overlap, like where this is positive and this is negative. So when this is positive and negative, that's a feasible design point. And of course, with the Piper Cub, it's very underpowered. I guess the things that really advanced aviation is engine power. So that was like the key to getting faster airplanes. Of course, the Piper Cub is a very slow basic airplane. So when this is positive and this is negative, that means, yeah, that's a feasible design point. That means I can have some forward motion and also lift my weight. So I also did some contour plots in Excel looking, yeah, this is a good area for the X force. That means I could generate positive force. So the trick here is I want to generate positive X force, but negative Z force. So that overcomes my weight. So this is the good area where I could overcome my weight as a function of airspeed of angle of attack. So it's telling me, yeah, this design is feasible, but not a very good performing aircraft at all. So this is the trick to this, to designing an airplane. So maybe I could possibly do some variations on different things to see if I could get more yellow. The more yellow I could get here, the better it would be. So some other things I did is I varied the altitude at 100 knots. So over here, this was at I believe it was one fixed angle of attack here. But let's see, my angle attack was still 1. So I always have a 1 in alpha and a -1 in the elevator to cancel out the effect from the elevator. So over here, I varied the altitude, and that's just done by the density. I went to the standard atmosphere table over here, and I cut and paste the density from 0 to I believe it was 1500 knots. So this is our air density over here in this column here. So I was able to cut and paste it into here, and then set at 100 knots. So from that, I made some more tables. Again, it's showing that at say 1 degree angle attack, where it's green means that it's positive. It means I can generate some forward force, but red is negative. It means I don't have enough power. But as you can see, as I go up in altitude, the force goes down, and likewise for altitude, as I go up in altitude, I want negative number here, but as I go up in altitude, this is like the lift. As I go up in altitude, that goes down also. So I did a similar thing for 80 knots, and at 80 knots, I actually have some. See, at 100 knots, I couldn't find, there was no overlap where I could have both forward force and negative Z force. So, but at 80 knots, I did find some points there. So it is a feasible design where even going up to 1,500 feet. Well, I couldn't get up to 1,500. The most I could get was 1,400 feet. So you start running out of forward speed. You can't overcome the drag forces, and you can't generate enough lift once I get over 14,000 feet. So anyway, that's an example of doing airplane design on a spreadsheet. So the last thing I have here are the moments. I'm trying to look at the moments to see if they're reasonable. So at 80 knots, this is an 80 knot airspeed at sea level. I wanted to vary a few things to see if it's feasible. If it's a feasible design relative to moments. So here I actually have 3 degrees of angle of attack. So I put a thing in here. I looked at it at 10 seconds. After 10 seconds, I wanted to see, is it reasonable? Like, do I build up good angular rates with changes? So right now, my angular rates are 0. So this is a case where it is feasible. Like I could generate forward velocity after 10 seconds. I would have a 179.94 foot per second change, and I could have some lift, an upward change of 59.12 feet per second. So I'm going to put in, say we put in some ailerons, say 10. Right now our moments are 0, but if I put in 10 degrees of aileron, I'm going to put that here and see what I get. I get so I get about a 3 degree per second roll rate, which is pretty reasonable after 10 seconds of input. So that's not fast, but it's a reasonable control there. If I was getting something very small, I might need to make the ailerons bigger. If I was getting something that was too big, then it would be oversensitive, the control power. So I might need to make the ailerons smaller. So I'm going to put that back to 0 again. And then the angular rate, roll rate goes down. So let's try an elevator. So I'm going to put in 0 here, which is like a 3 degree elevator change. So that gives me a 1 degree pitch up rate input. So that's kind of reasonable for a 10 degree elevator change. I might need a bigger elevator for this, but I guess being a Piper Cub, it's not very responsive in pitch. So we'll go back to -3 here. So now for the rudder, so we'll give that 10 degrees also. So a 10 degree change there causes the yaw rate of 1.32 degrees per second, which is probably reasonable for a Piper Cub after 10 seconds. So we do have some good moment control here. So anyway, this is how you could design an airplane configuration on an Excel spreadsheet. You could try different types of aircraft, bi-wing aircraft or triple wing aircraft, different elevators, different control systems. You could add flaps, you could add slats, all kinds of trim tabs, all kinds of things. So you could enhance this model and add more things as you go along, as you learn the aerodynamics, and then maybe variable pitch blades and variable pitch propellers. You could go on forever and ever and enhance this, but this is the basics of it, of what you need to do if you want to design an airplane. Thanks for listening to this, and good luck with your designs.